Alaikum. As I promised, I'm gonna make another video that is about your lab number PID. Okay, so as you can see, so PID tuning controller setting. We have a PID controller, PID controller whereby for PID controller there are three parameters. Set it to a value so that we get one that we want. Each of the value has effect on the one. That will be another. I will explain more about what is PID controller. But here is for us to determine the best value of K, the best value of tau I, the best value of tau D. Okay. The best value of KC that the response is achieve set point. Okay. Then value of tau I and tau D. For the value of KC, sometimes KC, sometimes but it's then the same thing, which is a proportional mode. So in industry, technically run, there's a lot of loops, a lot of control loops, okay, a thousand of variables that we want to control. We cannot tune single or manually. So we have machine run. Okay. For example, in a simple word, okay, in industry, there are 100 to 1,000 control loops. Say they have a lot of variables, 300 to 1,000. In order to each of the value of KC for each of the loop, each value of KC, tau I, and tau D for each loop would be very difficult and troublesome. Okay? So what people do is people do online tuning. Say when you have a machine or a actual plant, you tune there at that machine. Okay, what is tuning? Is to find the best value of C, tau I, and tau D. Okay, in order to get the best value, called tuning or adjusting. Okay, we adjust the value of AC. Okay, so for your lab number 8, it's actually that tuning. The difference is online tuning basically when we have a real plant, a physical plant or a physical machine. But for your lab is when we have software. Okay, like I told you before, there are three in this subject. Okay, you learn about theory in a class. You do a physical experimental in a lab, which is pH and temperature. That is a physical machine whereby you have there and also have a software. Okay? Can you differentiate between software, theory, and hardware? Okay? And the method, each of it represent the concept of same concept of it. So this is my lecture. It should be covered on maybe last my last lecture with you, but because really want, I know that you are so excited to know what is PID tuning, but it's okay, we can cover it now. Okay, so there are one method called a try and error method, or it's named as a continuous cycling method. Okay, closed loop method. This is what we do in the lab 8. The same procedure apply for the physical and the software. So later on, go you will cover on the map. If you can see, for the step number 1, after the process reach a steady state, you have to set the value of Ti equal to 0. What is this? Get the feature. So let's move our where. Okay. Start by opening a Simulink at a Simulink library. Okay. When we have this Simulink library, okay, don't forget to go to a new model. You have white blank space. Okay. So because we are talking about PID controller, why don't we go to PID first? Okay, just type PID, search for the PID. Here we go. Okay, this is a software named Simulink, MATLAB and Simulink, and this is a block diagram that represents a PID controller. If you double click this block, okay, this pop-up will come out whereby you can see here P, I, and D. Okay? So PID controller is about these three values. PID tuning is about to find what is the best value of PB, what is the best value of I, what is the best value of D. Okay, that is PID tuning all about. Okay, so moving on to our lab. Okay, moving on to our lab procedure. Okay, when you have lab number 8, it's about PID tuning. Okay, if you can see here for the GP is a transfer function. Transfer function is a mathematical equation that represents a process. So this process, okay, for this lab number 8, for this process, this is the transfer function that represents this process. So what we have to do, go back to our MATLAB. Okay, we're going to connect all the block. Okay, I want to close this first. Okay, so we have PID tuning here, and we also have a transfer function here. What we need to do is we're going to connect the controller and this transfer function so that it will form a feedback loop. Okay, so just go to FC. Okay, get that, get to click this button, this transfer function. As you can see in the module, you have you have three transfer function. So we can write function. Okay, that these three order transfer function represent everything. It already represent a transmitter, a control valve, a sensor. Okay, later on you will learn with me from a feedback loop. You will learn that we can simplify all the blocks in a single transfer function. Last time you learned a transfer function for a process, only. That is for your chapter 4 transfer function, for the process only. Later on you will learn with me the transmitter, the control valve, sensor also have their own transfer function. Okay? And these three transfer function is a combination of all that that feedback loop. Okay, so why don't we connect all the block? Okay, don't forget the source. Okay, source meaning to say an input. Just put step input here, step input, and then don't forget our thing scope, because you see the response graph. Okay, So next is we would like to correct this one. Just put it as 6. Okay. The one just remain as 1 for the numerator. Denominator, we adjust it. Okay. Okay. So we get this variable. Don't forget. Oh, I forgot something. Okay. Forgot to put a plus and minus. Okay, what is plus and minus? Block. Plus and minus block. You can find it at math operation. Have this plus and like here. Okay. I know some of you might asking me why we need plus and minus block here. As you all know, the controller comparison. The controller will compare the value of SB to the value of PB, or the other way around, the value of P to the value of SB. Okay. Because of the set point we have here is SB, because we set the value of SB, we set the value of SB, and then measured value is P. So it should be plus and minus. The difference between PB and SB is how much the error, how much the corrective action should be taken by the controller. Okay, in this boundary, okay, in this boundary is actually inside the controller. Okay, but in this one is a block representation which is in a software. Okay, so when we have the also want to compare, okay, we can hit the run button, but don't run away. Okay, at the first place, get kind of graph. When we see here, the meaning to say the simulation time from 0 to 10 is not enough. Okay, that's why you have to increase this one. Let me increase 100. Okay, when I increase to 100, okay, the graph is actually unstable, quite oscillating. What we need to do now is we go back to the method of tuning. Tuning by Ziegler-Nichols rules. Okay, I open back my PowerPoint. Okay, so based on this tuning method, yes, it is actually try and error procedure. You might be asking why we keep on changing of KC. Okay, here we have the value of P. Okay, we have to change the value of P. Okay, we have to change the value of P. We start with a small value first. Okay, and the value of tau I 0. Put it equal to 0 first. Okay, and then start with the value of P equal to 1. Remember, AC is equal to P is equal to have a relationship. Sometimes some of the machine using PB. So we start with the value of AC 0.5. Let's try 0.5. Click OK and hit the run button again. Start hitting the run button, this kind of response. Okay, for tuning to be successful, you have to refer to the step number 3. Okay, gradually increase the value of Kc until continuous cycling occur, meaning to say you get a sustained oscillation with constant amplitude. Okay, this is theoretically. Okay, this is the theoretically, and this is how people doing it. You just have to accept that. Okay, so we try to increase further the value of Kc or the value of P here. Okay, why don't we just increase to 0.8? Okay, hit the run button. In P, there are oscillation. Okay, more oscillation, more peak. That too. Okay, why don't we hit in 1? Okay, we see oscillation. Okay, and you have to be patient to try this. Okay, because that is the method. The 1.2, the response start to oscillate, but not yet sustained oscillation. What is sustained oscillation? Sustained oscillation is when you have a constant amplitude. Okay, 5, run button, E, 2, oscillate. Okay, but not yet sustained oscillation. Give a try again. And can put it not that high, a little bit higher, so you can start to see. Okay, I can increase further. First, okay, almost there, but the response start to be unstable. Might not need 1.7, we try 1.65. Okay, yes, we can have that, but the sharpness of the graph, until this point, I can see we already close to the correct value of C. Why don't I little bit? So that is 1.65 is bit another sustained oscillation. Okay, so we keep on trying to get the sustained oscillation, but you might wondering, is this a very good graph? What? But it does have a sustained oscillation rate. Let me adjust something that can get the graph we move line. What if I increase the value of simulation time? Try again. We can try. I will try to modify something so that we get graph. Okay. Once you get a sustained oscillation or something like this, okay, or even better than this, what you need to do is you have to substitute the value of uh, Kc, okay, the value of Kc or the value of P into the formula. Okay, is Kcu here. Okay, for PID tuning, just directly this formula 0.6 times 1.655. Okay, then what do you get? 0.6 times 1.655. You will get around 0.3. Okay. For the value of I or Pi, you have to measure the value of peak, the value of Pu or your lab module, it is Tn, the distance between the peak. Okay. How to measure that here? So we have to enlarge. If we can enlarge this. So you have to make it just take from this peak. Okay. Estimate about, okay, from this line to this line is 20, which is about uh maybe 16. Okay, just put it first. 16. Then divided by 2. 8. Then 10 divided by 2. Okay, we try. Try, don't worry. Because this is try and error. Okay. Obvious.